I'm the Philosophical Bachelor, and today I want to ask, is science true? What is real? Can science give us the answer? Or is science merely a bunch of models that work but may not correspond to reality? Is it even possible to know reality? The idea that science can and does give us the answer is a notion ingrained since one's early years of school. As a child, when we are taught things, they are taught to us not as ideas that may or may not be correct, but as facts, truths that we should learn and will be tested on. It is, of course, understandable why. To get to the postmodern destabilization of knowledge before we even have a good grasp of what is considered as knowledge is like a baby trying to run before it can crawl. Many of these facts remain with us into adulthood, mostly remaining unquestioned. The body of scientific knowledge seems to work reasonably well in our terrestrial setting, and hence we are not confused when we drop a ball and it falls to the floor and rebounds, the way Isaac Newton told us centuries ago. Even for the few that have some knowledge about relativity, the curvature of space-time does not come into play. The shortest distance being a straight line holds. We can see it for ourselves with our bare eyes, and it works in almost every setting a regular person is likely to encounter. Very few of us will become astronauts. So I suspect that the consensus position is that what science tells us is correct. This position is scientific realism, that what science teaches us is literally true. From forces to the entities these theories have, such as planets, stars, atoms, electrons, the ether, yes, all true. But what exactly is it that science even tells us? Unless one has advanced degrees in physics, I think most people hold the Newtonian paradigm of Euclidean space, light traveling in straight lines, and gravity as an action at a distance, which mystery we do not wonder too much about. It suffices to describe the world which we experience in our ordinary lives. Newtonian mechanics, however, is in conflict with the best science we have today, of quantum mechanics and general relativity. What does it even mean then to say that science gives us the truth? Which science? Newtonian mechanics works so well that for most of us, it is about the extent of the physics education we will receive. We now know that it does not present a correct picture of the universe, since it fails at the level of the very big and very small. But we also know that Newtonian mechanics works so well that we mostly need not care about how things really are. We may even acknowledge that it is a useful model that, while not true per se, works well enough. This view is anti-realist. It questions the common view, opposing scientific realism. Part of this opposition is to demonstrate that perhaps there is no way we can possibly know reality, and hence a fortiori, scientific knowledge cannot be about reality. While it may not present its own ontology, anti-realism presents viable alternatives that may suffice for our pragmatic purposes, given the limitations of our cognition. The belief that scientific theories are literally true, that the entities they postulate are real, and the relations between these entities are correct, and both describe reality, is known as scientific realism. For this essay, I rely on Michael Liston's entry in the Internet Encyclopedia of Philosophy. Scientific realism is characterized by these commitments. SR1. Science aims to give a literally true account of the world. SR2. To accept a theory is to believe it is true or at least approximately true. SR3. there is a determinate mind-independent and language-independent world. SR4, theories are literally true because their concepts latch onto or correspond to real properties such as natural kinds that causally underpin successful usage of the concepts. SR5, the progress of science asymptotically converges on a true account. Today, this seems to be the common sense position and hence the default way of understanding reality. That, for instance, an iron rod is real is unlikely to be disputed, but how about the electrons within it? Or the quarks within the proton within the nucleus? How about electromagnetic fields which are invisible to the eye? Those who oppose scientific realism are known as anti-realists, considering the scientific theories to perhaps be instrumentally useful but not quite true. Both sides have powerful arguments and the debate is current but not new. It began with the birth of modern science itself, the scientific revolution in the 17th century. Modern science is characterized by the mathematization of scientific theories and hence can be traced to René Descartes. Prior to the work of Nicolaus Copernicus and Galileo Galilei, the dominant understanding was that the Earth was at the center of the universe and the planets, stars, and sun orbited it. This is known as geocentrism and originates with Aristotle. However, the planets and stars do not seem to move the way they should according to geocentrism, and Claudius Ptolemy came up with a theory of epicycles to correct for these aberrations. What finally did solve the anomalies were the theories of Copernicus and Galileo, who posited heliocentrism, where the sun is at the center and the Earth just one of the planets orbiting it. Even at that time, some thinkers interpreted heliocentrism in an anti-realist way, conceding that while it did manage to save the phenomena, it is not literally correct or true. Galileo was, however, a realist on the matter, who in his trial by the Roman Inquisition publicly recanted his heliocentric belief under duress, but famously muttered, "And yet it moves." Today, we know that both theories are wrong. The Earth is not at the center of the universe, but neither is the Sun. Both the Sun and the Earth are in an obscure part of the universe, of which there may be no center to speak of. This brings us to an important argument for the anti-realists: pessimistic meta-induction. Theories that were dominant, mainstream, and widely accepted had later become defunct, overtaken by new, superior theories. Thomas Kuhn explains that as current orthodox theories become increasingly bogged down by anomalies, they have to be saved by ad hoc batches, leading to a crisis within the prevailing paradigm, which may then give way to an altogether new paradigm, which is revolutionarily different from the one it overtook. Geocentrism is a case where this happened, with Ptolemy's epicycle being the ad hoc patch and heliocentrism being the revolution, which was strongly resisted at first but later became the dominant cosmological theory. The anti-realist read on this account of the history of science is that what was taken as true and correct earlier became considered false and wrong later. Since this has happened many times in the history of science, by induction it will happen again. That is why it is a pessimistic meta-induction. Today's dominant orthodox and widely accepted theories are likely to suffer the same fate, and therefore there is no reason to believe that what they posit, specifically the entities they devise as part of their theories, to be true. Today, atoms and molecules are taught in school to be the basic constituents of matter. In higher education, fundamental particles such as quarks and gluons are accepted as part of the standard model of particle physics, alongside dark matter, dark energy, and black holes. All of these entities are stuff that we cannot observe with our bare eyes, and some of them, like dark matter and dark energy, we cannot detect even with our most technologically advanced instruments. Yet realists, since they believe that scientific theories give a literally true picture of the world, will have to accept that these are real. When we see a table, building, rock, or animal, we should remember that according to science, they are constituted of atoms which are constituted of the fundamental particles. A competing position is that of empiricism. Empiricists argue that we can only be confident of what our sense faculties can detect, which means that what cannot be verified or demonstrated through experiments and experience cannot be accepted. This also seems reasonable, but that would mean ruling out much of what is considered orthodox science today. Another position is skepticism. As articulated by Immanuel Kant in his Transcendental Idealism, we never experience directly the external world. What we perceive through our senses has to be processed through the faculty of our understanding, which are structured by categories, space, and time, which are a priori, in order to make sense of them. The output of these processes gives us representations, but whether these representations resemble the real world accurately or at all is unknown and, according to Kant, unknowable. All we can know is phenomena. We can never know the noumena. In yet another position, Henri Poincaré proposes that there is no fact of the matter. What we accept to be valid is a matter of convention. Liston, however, informs us that conventionalism is not an anything goes doctrine. Not all stipulations will accommodate the evidence. It is the claim that the physical meaning of measurements and evidence is determined by conventionally adopted frameworks. Conventions are adopted for pragmatic reasons, because they make physics simpler, more tractable, and more familiar. Such conventions include how our geometry is Euclidean. Since, in yet another convention, light travels by the shortest path, in a Euclidean geometric world, that will mean that light travels in straight lines. Empiricism or experimentation is unable to help us check this, because experiments only have physical meaning relative to the conventions. Yet, a belief in scientific realism is difficult to shake because of the no miracles argument as proposed by Hilary Putnam. Because science is so effective at predicting the results of experiments with such high accuracy and allows us to manipulate phenomena to serve our material purposes, if what they posit were not true, at least approximately, it would require miraculous coincidences. While persuasive, the conclusion of the no miracles argument does not follow from its premises. Even untrue theories can provide accurate results and allow technologies to be built based on them, such as Newtonian mechanics. The scientific world mostly agrees that the best theories of physics currently are general relativity to explain phenomena at the cosmic scale and quantum mechanics at the subatomic scale. Newtonian mechanics has been overtaken, and while useful for working out many terrestrial and planetary phenomena, is basically wrong. In addition, some entities postulated by some theories only work in certain conditions. While the existence of atoms may explain some phenomena well, such as the kinetic theory of gases explaining the macroscopic properties of pressure and temperature in gases, they are unable to explain or be used to predict other phenomena such as electromagnetism, thermodynamics, and heat transfer. Concepts such as energy, force, action, entropy, and temperature are not well grounded by classical mechanics, depending on general analytical principles such as the conservation of energy, momentum, and mass, which are not derivable from Newtonian mechanics governing classical atoms. Liston remarks, "Many thought that physics has become a disorganized patchwork of poorly understood theories, lacking coherence, unity, empirical determinacy, and adequate foundations. One may hence become a local anti-realist, disbelieving the posited entities of specific theories, which while instrumentally useful are not literally real, while not losing hope that there is something real which ultimately can be discovered through science. Some others may be global anti-realists, who do not think that scientific theories, no matter how unified, explanatorily complete, or fundamental, can tell us anything about the underlying reality. In fact, they question whether science should even have such a goal. For the scientists who have such a realist goal, what is being searched for are causal explanations down to the most fundamental levels, be they atoms, fundamental particles, or fields. For other scientists with an instrumentalist viewpoint, being able to describe phenomena with mathematical laws may be sufficient, or even the best that can be hoped for. Some scientific theorizing has indeed proceeded down such a path, such as the phenomenological theories of thermodynamics and energetics, which provides abstract mathematical organizations of the phenomena without inquiring into their causes. This follows the deductive nomological or covering law model of science articulated by Carl Hempel, where phenomena is explained by deducing them from scientific laws and initial conditions. Law-like regularities are observed between certain types of events. If an event of type A occurs, an event of type B occurs. An event of type A occurs, the deduction is hence that an event of type B will occur. Once a phenomenon can be reduced to its governing nomos or law operating on initial conditions to give the correct calculated empirical outcome, it is considered explained. To ask why A causes B is not a valid question under this model. Hempel is a member of the logical positivists, an influential group of thinkers from the 1920s to 1960s. Their aim was to ground science on a firm empirical footing with verification as the core principle of knowledge. They considered science with its aim to organize and predict observable phenomena as a legitimate enterprise, while metaphysics, which aims to discover the underlying nature of reality, to be illegitimate, since the fundaments it posits are unobservable and hence unverifiable. Hempel's deductive nomological model is one of their results that remain with us today, where metaphysical causes are replaced with explanations based on law-like correlations. They are anti-realist to the extent that theoretical entities are understood as a function of their law-like logical relations to other entities, both theoretical and observable ones. They deny metaphysical interpretations of these entities. For instance, that atoms cause phenomena. All there is to being a real physical object is its empirical reality, its system of relations to verifiable experience. Note listed. How the logical positivists do this logically is to take the meaning of any sentence to be its verification conditions. To understand a science is to understand how its assertion can be verified. This approach is common sense for the sensible things we can observe. For instance, the car is blue can be verified by observing that the object indicated is indeed a car and that that object is blue in color. However, unobservable entities cannot be verified directly since they are unobservable. The positivists try to overcome this problem by distinguishing two types of linguistic terms: observational terms or O terms and theoretical terms or T terms, such as electrons. If a T term can be explicitly defined by O terms, then to verify the T term is simply to understand the verifiable conditions of the O terms used to define it. A theory's theoretical content would then be just its observational content, notes listed. Say we have a T term, pray, that is defined by having 4 wheels and an engine, is driven by a human being and uses petroleum. The T term is then completely specified by the O terms wheels, engine, human being, and petroleum. The hope is that a reductio can be achieved where those other T terms can ultimately be defined in O terms, which would then make a theory completely explicable in terms of O terms and their relations. The difficulty arises when T terms are not completely defined by O terms. For instance, atoms, molecules, quarks, gluons, and electrons. Rudolf Carnap, a leading member of the logical positivists, proposes that this problem can be overcome. The meaning of a T term is given by the logical role it plays in a theory. The totality of their logical connections within the theory to other T terms and O terms specifies their meaning. However, one problem is that O terms and T terms are often mixed together inseparably. O terms can apply to T terms, for example, tiny electrons, and T terms can apply to O terms, for example, the power of the car's engine. In addition, there is no clear distinction between what is observable and not observable. If something is observed using instruments like microscopes, does that make the entity observable so that we can trust the evidence of our senses? Besides, detection can occur in indirect ways. For instance, we detect gravity through its effects, say when we drop an object and it falls. We cannot see gravity directly. How would the T term gravity feature for the logical positivists, since it is not directly observable? Liston writes, the positivists may respond that they cannot be directly sensed and are thus unobservable, but why should being directly sensed be the criterion for epistemological or semantic confidence? In addition, observation is theory-laden. How we understand our observations is a function of the language, concepts, and theories we possess. A caveman who sees an airplane flying in the sky may perhaps think of it as a kind of bird and not a non-living artifact powered by jet fuel. To draw a clear separation between observation and theory is untenable since they are inseparable. Willard van Orman Quine proposes a series of arguments that counters the verificationism of the logical positivists. Our evidence for unobservables is similar to our evidence for observables. In each case, we have a theory that posits an arrangement of objects that organizes our experience in a way that is simple, familiar, predictive, covering, and fecund. This is just what it is to have evidence for something. So if we have such an organizing theory for molecules, then we can no more doubt the existence of molecules than we can doubt the existence of ordinary physical bodies, he writes. In addition, according to the Quine-Diltham thesis, only a group of hypotheses can be falsified because only a group of hypotheses has observational consequences. A single hypothesis by itself may not have any observational consequences. It requires the support of auxiliary hypotheses or assumptions. Say the hypothesis that water boils at 100 degrees Celsius. This is true only if there are supporting conditions, such as the experiment taking place at atmospheric pressure, the water is pure, the thermometer measuring the temperature is working properly, that boiling is when there is a phase change between liquid and gas, and more hypotheses on the way of observing that. If in our experiment water did not boil at 100 degrees, we can only say the hypothesis and assumptions as a group is false. Maybe water does boil at 100 degrees, but the thermometer was broken, for instance. Just because our experiment did not observe water boiling at 100 degrees, we cannot conclude that our hypothesis is false, since it may be that one or more of the auxiliary assumptions or hypotheses were false instead. Likewise, we cannot say our hypothesis is true just because the experimental observation showed that water boiled at 100 degrees. Perhaps because our hypothesis is false, but an auxiliary assumption was also false, leading to the experimental result. Hence, even in the face of this confirming evidence, any statement can still be held to be true. Another example involves the use of instrumentation. We look at a cell with a microscope and observe that the cell is blue. However, that percept depends on the auxiliary hypothesis concerning how the microscope works, optics theory, the theory of light, and the theory of how our eyes and cognitive apparatus work. If any of these theories or apparatus fail, then our observation is false. For instance, if the observer was wearing blue spectacles, the light in the laboratory was not white but had a blue tinge, or the microscope's lens had been stained by a blue liquid, which now makes everything appear blue. To hypothesize that the cell is blue requires not just that the cell is indeed blue, but also a string of accompanying auxiliary hypotheses and assumptions such as the microscope is working properly, the light in the laboratory is white, the observer's glasses are not colored, etc. Verification hence cannot be made of a hypothesis, but only on a group of them. In any case, the separation between science and metaphysics as insisted on by the logical positivists is hard to make. The standard of evidence remains whether the entities posited by science or metaphysics contribute to a useful organization of experience and whether they stand the test of experience. The realists claim that scientific realism is the best explanation for the success of science and scientific practice, and hence, based on an inference to the best explanation, or IBE, scientific realism must be correct. The question, however, is what constitutes the best explanation. Liston clarifies that while the most likely explanation is the best, likelihood is only knowable ex post. It is also not merely what is the best available, since that may make it the best of a bad lot. Hence, what makes for the best explanation must instead rely on epistemic virtues such as wide scope and precision. It appeals to plausible mechanisms. It is simple, smooth, elegant, and non-ad hoc, and it underwrites contrast. Why this rather than that? However, why should nature care that we like epistemically virtuous theories? Do simpler, smoother, more elegant, and non-ad hoc, more unified theories make them more likely to be true? Nature need not be simple, smooth, elegant, and unified. IBE cuts no ice with anti-realists in any case, since they ab initio question any connection between explanatory success and approximate truth. Besides, the success of science need not necessarily be attributed to scientific realism. It could simply be a Darwinian selection of successful theories and discarding of unsuccessful ones. However, in practice, theories make unexpected novel predictions, hence imperiling their chances of success. In any case, what is best is obviously debatable since there are a slew of other explanations that their proponents will probably consider to be the best. One such explanation is constructive empiricism, an anti-realist view proposed by Bas van Fraassen, where the aim of science is not to give a literally true account of the world, as scientific realists believe, but to provide empirically adequate theories of the phenomena. It is a pragmatic approach where science is considered to have progressed when it produces increasing empirical adequacy. To be empirically adequate, a theory has to represent all the phenomena, though it need not necessarily be true. It is hence a non-epistemic approach, since an epistemic approach is about true or false beliefs. Agnostic about truth value and unobservables, for constructive empiricists, commitments are neither true nor false. they are either vindicated or not. If two different theories are equally empirically adequate, the one to prefer is a pragmatic choice, the pragmatic choice being to prefer the simpler or more convenient theory. Once again, a difficulty with the theory of constructive empiricism is the distinction drawn between observables and unobservables. Why should inferences be limited only to what is observable when there can be similarly good evidence for unobservables? Liston asks, why is it legitimate to infer the presence of mice from causal observation of their telltale signs, but illegitimate to infer the presence of electrons from careful and meticulous observation of their telltale ionized cloud chamber tracks? Besides, our experiences are limited. Why should we generalize from this limited experience and not likewise generalize from data on unobservables which are detected through reliable instruments or calculable with reliable theories? In addition, observations are theory-laden. It is the theory that tells us what is observable and what is not observable. Why should we believe what it says about observables and then be agnostic about what it says about unobservables? And why should we believe that it is right when it tells us what is observable and what is unobservable? Constructive empiricism may thus be self-defeating. There are generally two types of challenges to scientific realism: historical and semantic. SR5 states that the progress of science is symptotically convergence of a true account. However, is science progressive? The history of science does not seem to vindicate this view, according to Kuhn. Instead of progressive, the history of science is discontinuous. There are long periods of normal science which operates in one paradigm. However, as with the example of geocentrism, anomalies accumulate leading to a crisis in the paradigm. This crisis is only resolved by a revolutionary new paradigm that is incommensurable with the old paradigm. Since the two paradigms are incommensurable, it is hard to say if there has been progress since they cannot be compared. However, if epistemic virtues are what determine if there has been progress, progress can then be measured in terms of accuracy, consistency, scope, fecundity, and simplicity. These, however, are soft factors, which is not necessarily a bad thing, since it is this softness which enables new theories to get off the ground. Progress can be made only if there are values to allow rational discussion and argument, but not hard rules that will predetermine an answer, because then everyone would conform to the rule and not risk proposing new alternatives. Pessimistic meta-induction has already been mentioned. Loudon argues that referential success is neither necessary nor sufficient for empirical success. Not necessary because the central terms of many successful theories did not refer, like 19th century ether, caloric, and phlogiston theories, for example. Not sufficient because the central terms of many failing theories did, by our lights, refer, like 18th century chemical atomism, Wegener theory of continental drift. A convergence towards truth is problematic because it is unmeasurable since no metric exists to do the measuring. Some newer theories can encapsulate older theories. Newtonian mechanics are limit cases for Albert Einstein's general relativity, and hence general relativity is superior. But for others, such as Anton Laurent Lavoisier's oxygen theory as successor to Joseph Priestley's phlogiston theory, there are no analogous limit theorems. Besides, the same terms such as mass in classical mechanics and relativity refers to different things in the sense that they have different meanings, and so it is hard to say that relativity provides a more global picture. What limit theorems show is that some structure of abstract relations is preserved. I will discuss structural realism later. More recently, Carl Stanford's new induction raises the problem of unconceived alternatives, where at any given time there are alternative scientific hypotheses not entertained, but which are consistent and even equally confirmed by all the actual evidence available. In principle, if realists did know about both, they would have no way to decide which is better. Stanford argues that his new induction reflects the history of science, where earlier theorists selected a particular theory, T, only for it to be overtaken by a new theory, T star, which supports the evidence equally well or better. If both theories had been available at the same time, they would have gone for T star. Since both cannot be correct, scientific realism on T star would mean anti-realism on T. Semantic Challenges is about meaning of words. As SR4 tells us, theories are literally true partly because their concepts latch onto or correspond to real properties, natural kinds and the like, that causally underpin successful usage of the concepts. Hence, the entities of scientific theories should be able to refer to something in the world. This correspondence is expected because we use representations of our environments to perform tasks. Truth is hence a causal explanatory notion. Semantic deflationists, however, point out that truth and references are merely disquotational. The word electrons points to electrons, regardless whether our belief in electrons is true or false. In that case, truth is not an explanatory notion. Kant's transcendental idealism posits that we can never get beyond phenomena to the thing in itself. Hence, we cannot know SR3, where there is a relation between our representations and a mind-independent world, since we lack direct access to that world. The words we use are not between word and world, but between word and phenomenon or object as conceived by us. This is known as internal realism, true in the ideal theory which falls short of true per se. Structural realism shifts the focus from the entities that scientific realists believe to be true to a position where, regardless of whether the entities exist, the structure of the relations espoused by the theories do correspond to the structure of reality. These structures are expressed by the mathematical equations of the theories such that the relation holds regardless of the status of the nature of the entities represented by the variables of the equations. According to structural realism, science aims to describe only the structure of the objects but not their intrinsic natures, making structural realism a kind of middle way between scientific realism and anti-realism. While pessimistic meta-induction argues against the reality of the unobservables, since previous theories have come to be proven false, optimistic meta-induction argues that past successful theories have been approximately true, with newer, more successful theories approaching ever closer to the truth. Structuralists hold that though ontologies come and go, our grip on the underlying structure of the world steadily improves as the mathematical structure is preserved and improved on. For instance, Augustin Jean Fresnel's structure of light as wave phenomenon is retained, while its nature as a vibration in ether is discarded. However, can structure be rendered intelligible without the ontology that gives them flesh? This can be answered from an epistemological and an ontological angle. In epistemological structural realism, while unobservables are objects, science cannot discover their nature other than their structural relations, compared to how both nature and structure can be known for observables. However, the observable-unobservable distinction is problematic since observables may, for instance, be made of non-observables, like a table is made of atoms. Critics argue that our knowledge of the nature of unobservables, such as electrons, is bound up with our knowledge of their structural relations, so that we come to know them together. Saying what an electron is includes saying how it is structured. Ontological structuralism argues that we can know only structure because only structure exists. This view resonates with process philosophy, where there are no substances, only processes. It does away with objects altogether, even as structural notes in epistemological structural realism. As with process philosophy, the difficulty is to accept its key premise, that structure or process is all that exists. Structural realism is a selective realism in the sense that it argues that the good features, structure, is preserved, while the bad features, like the nature of entities, is discarded. There are other types of selective realism, for instance, referring successfully to an unobservable while having false beliefs about it. For example, Fresnel and James Clerk Maxwell talking about ether when they may mean the electromagnetic field. Anjan Chakravarti proposes semi-realism, where detection properties are causal properties well confirmed by experiments because they underwrite the causal interactions we and our instruments exploit in experimental setups, with auxiliary properties only serving as theoretical and inferential aids. In semi-realism, the detection properties are retained in theory changes, while the auxiliary are not. Is this, however, really possible given the Quine-Duhem thesis? These strategies attempt to cherry-pick the various aspects of scientific theories they consider enduring and discarding the rest. However, since the causal entities across different theories have differing natures, how can they somehow continue their relations across the theories? Besides, how does one decide which features are good or bad, other than through hindsight? We simply do not know what they are for our current theories, since if we did, we would already have discarded the bad, and hence we would have already arrived at perfect theories. Whichever parts selective realists select are hence not free of problems. For structural realism, the relations are preserved. Nancy Cartwright focuses her attack on these relations. As an anti-realist about scientific laws, she asserts that the laws of physics lie. The laws of science do not describe nature, but idealized objects in abstract mathematical models. There do not exist in nature the idealizations that theories presuppose, such as pure materials, or the existence only of singular forces to the exclusion of any other, such as a gravitational system without, say, an electromagnetic system. Only messy phenomenological laws describing empirical regularities and fairly directly supported by experiment truly describe natural systems, adds Liston. Theories simply ignore disturbing forces that do not fit, explaining them away as negligible or mathematically incorporating them but inconsistently. Intelligibility, not truth, is hence the goal of theoretical explanation, observes Liston. Cartwright suggests that while we may have to give up the hope that theoretical explanations are true, we can instead infer to the most likely cause, which then justifies belief in unobservables that are experimentally detectable as the causes of phenomena. Hence, we should be anti-realist about fundamental laws which are not even approximately true, but be realist about unobservables. The hope of a true unified explanatory theory of physics is either based on a misunderstanding of physics practice or a vestige of 17th century metaphysical hankering for a neatly designed mechanical universe, explains Liston. Critics respond that the quest for unity is a powerful force guiding progress in physics, with theories such as Einstein's unifying Newtonian mechanics with electromagnetism. As for inference to the most likely cause, the most likely cause may not exist, in the same way that the best explanation may be false, for example in the case of the caloric and phlogiston. One reason why selective realism does not seem to work is that the entities and structure of a theory are bound together. Theories are not a collection of parts thrown together in a bag, but are more like the fabric of the bag with the parts sewn into the fabric. Holes in the fabric may eventually cause the entire bag to unravel altogether. It is why scientific realists insist on taking entire theories as true, or at least approximately true, with the hope ultimately of converging on the truth as theories improve. The difficulty is that we do not know how close we are, or for that matter if we are even on the right track. New paradigms overthrow the old in a discontinuous way, so the trajectory of science does not seem to be ever upwards, but instead all over the place. The big question is whether the aim of science is ultimately pragmatic or ontological. If pragmatic, so long as it works instrumentally to serve our purposes, be it building new technologies or easing our way of life, it may not matter at least in the near term. If the enterprise of science is to find the truth, then even if a theory works well to serve our needs but is not truth-enhancing, its value is decreased. Importantly, if the ontology of the theory is wrong, we will sooner or later run up against the theory's limitations, which then restrict its instrumental value also. We see this clearly with Newtonian mechanics, which has been a tremendous boon in industrialization, but which fails when we explore deeper into the very big and very small. We should, however, note that realism is not essentialism. Realism is the view that science aims to explain phenomena, while essentialism is the view that science aims to find theories that are fundamentally self-explanatory in a quest to explain every regularity. Societal attitudes towards the question matter. Up to a certain point in a country's economic development, instrumental value may be the priority, but once the major needs have been satisfied, truth for truth's sake may come to be crucial. The pursuit of truth also has pragmatic purposes, but serve the longer term. However, if the short term cannot be secured, then to care about the longer term may be misguided. The morale of those working in science must also not be ignored. To build a functional model brings its own satisfaction surely, but to discover eternal truths bring us closer to the divine. Thank you for listening to the Philosophical Bachelor.